paper. The first one is a full row reduction in the multi-party case for both multi-party garbled circuit blueprints, so the HSS 17 style, and also authenticated garbling. And in both versions, we reduced the number of ciphertexts that you need to send per AND gate from 4 to 3. So this improves over the previous schemes from 4n times kappa, so n is the number of parties, and kappa is the number of bits per wire label. In the HSS 17 style, to 3n kappa, and from 4n minus 6 kappa in the authenticated garbling to 3n minus 1 kappa. And achieving this full row reduction in this setting has been formulated as an open problem by Wang et al. In CCS 2017, and we solve this now. The second contribution concerns the preprocessing that we need to set up and be ready for the garbling phase. And there we generalized the approach by Dittmer et al. From Crypto 2022 to the multi-party case, and this improves the communication cost for large circuits. But first, I will give you an introduction about two-party garbled circuits, and then I will show you how the blueprint for authenticated multi-party garbled circuits work. And afterwards, I will come to the construction, and then maybe if I have time, about the preprocessing and then some numbers. So we use two-party garbled circuits to do secure computation with a constant number of rounds. And so we have two parties, the garbler and the evaluator, and they share a Boolean circuit that they want to securely compute. And because of previous works that make XOR gates basically for free, we are only concerned with AND gates. So the garbler starts by drawing a random offset string delta for the whole circuit, and then for each wire in the circuit also samples a uniformly random wire label base key. And then we can encode bits as follows. If we want to encode a 0, then we just use this KA0 label. And if we want to encode a 1, then we use KA0 plus this delta. This allows us to get XOR operations for basically for free. And then what we want in the end is that if the evaluator only has one of the two keys for the input wire labels, so for instance, he has the key for alpha and the key for beta, then we want to send the evaluator some information that he is able to get the right output wire label key. And to do this, the garbler prepares the garbled circuit, which is an encryption of the right output label key, encrypted using the right input wire keys. And then, since the evaluator only has exactly the keys for one row in this circuit, he can decrypt this row correctly and then obtain the right output label, in this case, KC of A and B. And what I didn't do here in the slides is that we have to also permute the circuit, otherwise, like the order of the rows, otherwise it's not secure. But I will skip this for simplicity. The main bottleneck in this computation is, or the main communication bottleneck here is the size of the garbled circuit. So how many rows we have to send. And to reduce this, this is called a row reduction. And in the two-party setting, this was already studied by Nauer et al. In 99. And they observed that instead of choosing this wire label uniformly at random, they choose it as a function of the input labels, in particular like this. So if they choose it as this term in a simplified way, then you can see that the first term, everything cancels out. And this is a 0, so we don't need to send it. And this will mean that we have only 3 rows left, so we have reduced the circuit size. So in the two-party setting, this is nice. The garbler now can compute this KC0 wire label as a function of the input wires. This reduces the degree of freedom in the garbling equation. And this means that he cannot choose all of these KC0 values for all the AND gates in the circuit at the same time. In the two-party setting, this is not a problem because the garbler can just compute, go step through the circuit and then send the garbled circuit afterwards. But in the multi-party setting, this is no longer possible because we want to garble all the AND gates at the same time. And this is the reason why row reduction in the multi-party setting is more difficult to do. So how does it work in the multi-party setting? So the garbler knows too much information about the circuit. So this means that we distribute the role of the garbler among all the parties. And in the authenticated garbling blueprint, the parties, they prepare shares of each other party's garbled circuit, and they also prepare shares of some authentication circuit that helps the evaluator assess that everything happened correctly. And the setting that we target here is active security with a dishonest majority. So we have like n-1 garbled circuits that are jointly computed in the garbling phase by the n parties, and then we have one party that evaluates. To be more concrete, for every wire, instead of directly encoding a 0-bit and a 1-bit in this pair of keys, we now have another layer of indirection. We have this random mask lambda that masks the encoded value. And then the parties, they only observe this A hat, which is the external value. And since we're in the active security setting, we also we have authenticated bit shares, which are bit shares that have a pairwise MAC sharing between all the parties. And we use the same data as both the MAC key and also as the free XOR offset for our encoding, which makes things very convenient because then you can just, from these terms, you can directly compute shares of the garbled circuits. And then to compute an AND gate in the normal way, you would compute four values following this equation. And this equation is something that we want to transfer to the evaluator at the end. So it is exactly like alpha times beta, so exactly the value that we want the evaluator in the end to have, masked by a fresh random mask. So this is what we want the evaluator to obtain at the end. And then what we do is we will encrypt this. So we will encrypt the blue part, which is the bit share of this masked output bit. And then we also encrypt some information so that the evaluator can obtain the correct encryption key for the next gate. So this is the garbled circuit for each party. And then also some authentication information that the evaluator can use to check the correctness of this term. And then the evaluator, given an active key, or given n-1 active keys for each of the input wire labels, for each of the input wires can decrypt exactly one of these rows, and then obtain the external output value from the blue part, obtain the active keys to continue the computation from the orange part, and also can check the correctness of this equation that we want to have in the end from the purple part. And then follow-up work have managed to remove sending the blue and the purple part in the garbled circuit at the expense of doing some additional interaction after sending the garbled circuit and after the evaluation phase. Okay, and so now I will briefly summarize our idea for the row reduction. So we split this AND equation into three parts. One is called product 1, the other one is called product 2, and then we have some parts that only depend on the masks. So, and product 1 is the external value of A times beta, so the real input. Product 2 is the external value of B times the mask, and then these mask terms. And if we look at it, product 1, for product 1 we need to compute using both wires, but product 2 is only depends on beta. It does not depend on alpha at all. So therefore, this is a unary gate. And then what I will show you now is that we can apply a row reduction for this gate. This leaves some undesired offset artifacts behind, which we can then subsequently correct in the other gate. And then since we XOR them together, this offset will cancel out and we get the correct output. So to compute the product 1 gate, you can think of this as a multi-party version of one of the half gates, or equivalently a multi-party version of this one-hot garbling construction from Heath et al. Boiled down to the length 2. So the parties, they hold an authenticated sharing of this lambda. And then they do essentially, they compute this one ciphertext, they put in the bit share of this value that they want the evaluator to have, something that looks a bit like a properly defined wire key and authentication information. And then the evaluator can, and I forget. So, and we encrypt this with both the 0 and the 1 key. And then the evaluator computes the encryption of the key that he has, and then conditionally adds in the ciphertext and the active key for B. And if you expand this, then you will see that this gives you correctly a share of this product 1 gadget that we want, and also the right authentication information, but the middle part is somehow incorrect because it correctly encodes the value that we want, but it also has this undesired offset that I marked here in red. And the problem is that at this moment, no party alone can undo this offset. So this is why we will correct it in the other gate. And the other gate is just a regular unary gate that is garbled in the same way as the authenticated garbling. So, so we will compute 2 ciphertexts. Both of them are encrypted with the 0 and the 1 key. And then we encrypt the blue component, the orange component, and the purple component. But we also add in this, this offset value. And then the evaluator computes this normal decryption by picking one of the 2 ciphertexts and then just decrypts it. And if you then XOR these together, then the red parts will cancel out, and then we have basically transferred this AND equation to the evaluator at the end. And so the evaluator gets a freshly masked value of alpha times beta in the blue component, and then also the right output keys to continue the computation. So to summarize, we do a row reduction in this first part. This costs us only 1 ciphertext. And then we correct this offset that is left behind here. We correct it in the second part, which costs us to garble normally 2 ciphertexts because it's a unary gate. Then I will briefly talk about the preprocessing. So in multi-party garbled circuits, the preprocessing can be partitioned into 2 phases, the function independent and the function dependent preprocessing. And in the function independent one, we just generate authenticated bit multiplication triples, which we then later use to multiply the 2 lambda values together, and which one of them depends on how the circuit looks like, or which AND gates interact. And then this product we use for the garbling. And in previous work, this function independent preprocessing is quite expensive because we need to produce random authenticated bit triples. On the other hand, the function dependent preprocessing is very cheap because you can do a beaver multiplication on bits. So you just send 2 bits and you can amortize all the checks. And the approach by Dittmer et al., which we then extend also to the multi-party setting, takes a different approach. They generate, or we generate large field authenticated multiplication triples. And this is something we know how to do with sublinear communication cost. And then we use these to multiply these 2 bit shares together. But this is a large field multiplication, so therefore we have to pay, in this phase here, we have to pay more than just bits. But we can choose this field to be smaller than the kappa bits. So concretely, what we do is we design a PCG protocol for some correlation, for some authenticated multiplication correlation. And then we perform a large field multiplication to multiply the lambda lambda A and lambda B values. And then, since we are still in the smaller field F2 to the row, we key switch this authentication key from F2 to the row to F2 to the kappa, using also like an N-party VOLE protocol, which is also very efficient in communication. This is described in the full paper. So to summarize, we have two contributions. The full row reduction is gives us 25 to 43% smaller circuits, depending on what you compare against. And we have implemented this garbling phase and also the evaluation phase for the authenticated garbling protocol. And it is not slower than the previous state of the art. So this is a net win. You don't pay in execution time, and it also uses less communication. On the other hand, we improve the preprocessing. We introduce these sublinear techniques, and this gives us a 6 times communication cost improvement over HSS17 and 2.2 times lower communication cost compared to the previous authenticated garbling. And that's the end of my talk. So you can find the ePrint here, and I'm happy to answer questions.
Any questions from the audience? Okay. People might be starting the session a little bit shy, so I'll ask a question. So do you think you can go all the way to match half gates in the multi-party setting to get 2 ciphertexts per gate?
So basically what half gates does is it computes a half gate here, right? And a half gate here. And then these masks, they can be just injected for free by the garbler, because the garbler knows all of them and it can just add them to the outputs. Well, how I think about it is that, so it is possible to also have a row reduction here, which also leave some offset, and then you would need an additional term to just correct the offset, like an additional ciphertext to correct the offset, and then add the mask values. So this also gives you 3 ciphertexts. So this is not better. I would guess maybe that if you use the this slicing and dicing, that maybe you can go to 2.5. Because you still need like 1 ciphertext to get like to include the mask values. But this is my intuition. I have nothing that shows otherwise. Yeah.
Something maybe related to this. So am I right in understanding that the savings of like 1 ciphertext comes from like the structure of using half gates,
Yes.
as opposed to like it's a different technique than say the sort of the classic row reduction, like from before half gates, where you have 2 different, where you're just hashing your inputs together.
Mm-hmm.
Okay. So yeah, it seems like maybe in that context, then maybe you always need this like 1 extra ciphertext compared to the usual straightforward 2-party gate garbling case, because you need to like have this offset you were saying.
Yes, I think so. Yeah.
Yeah. So maybe that's just the observation I wanted to mention.
Okay.
Okay, it looks like there are no other questions, so let's thank the speaker again. Right, so the next talk in the session is about multi-party garbling from OT with linear scaling and RAM support. It's a paper by David Heath, Vlad Kolesnikov, Varun Narayanan, Raphael Ostrovsky, and Akash Shah. Akash will give the talk.
Thank you for the introduction. This is a joint work with David, Vlad, Varun, and Rafi. Let me first introduce the notion of secure multi-party computation. Here you have n parties. Each party Pi holds input xi, and parties want to compute the function f privately. And there is an adversary A that corrupts at most t of this n parties. And the security requirement is that the adversary should learn no information about the private inputs of honest parties beyond the output of the computation. And in this work, we consider malicious security with a bot. Garbled Circuits was introduced by Yao, which is an efficient two-party computation protocol. So it garbles a Boolean circuit gate by gate. That is, it encodes each gate as an encryption of the row of its truth table. And the nice feature about garbled circuits is that it is constant round and it makes black box use of AES, which is supported by modern hardware chips. BMR extends garbling to the multi-party setting, and their idea is to make use of an MPC protocol in the pre-processing phase that garbles all the gates of the circuits in parallel. And this way, they obtain a protocol that is constant round and that makes black box use of AES. However, this protocol is secure in the semi-honest setting, and the communications cost is order n square kappa. Then there is this line of work in the malicious security setting. The initial works had quartic and cubic overhead. Then there was the work by Wong et al. And Haze et al. That constructed concretely efficient multi-party garbling scheme, assuming random oracle and oblivious transfer, but the communication cost was order n square kappa per gate. Then recently, there have been works assuming LPN and DDH, where the communication cost per gate is order n kappa and order kappa. And I would like to point out that the work of Beck et al. Is in the honest majority setting. So to summarize, this is the state of the art in the dishonest majority setting. So you have schemes that are based on random oracle and oblivious transfer, but the communication cost per gate is order n square kappa. Then you have schemes that have linear overhead, but they assume LPN or DDH. So in this work, we asked this question that can we obtain a garbling scheme with order n kappa overhead that makes just black box use of random oracle and OT. So we answer this question in the affirmative in this case for the dishonest majority setting. However, we require a fraction of parties to be honest. The second result is in the context of garbled RAM. This extends garbling to random access machines, and it garbles RAM program with quasi-linear overhead. In the two-party setting, there have been constructions to obtain practically efficient garbled RAM, and the next talk is actually going to be in this space. And in the case of multi-party garbling scheme, you have a work by Gerg et al., which constructs a garbled RAM scheme with n polylog overhead. However, this is a feasibility result, and in this work, we construct a concretely efficient multi-party authenticated garbled RAM, assuming random oracle and oblivious transfer, and the communication overhead is n log cube kappa, and the corruption threshold is n1 minus epsilon, that is the dishonest majority setting. So our work builds upon the work of WRK. So in WRK, at a high level, for those who are familiar with the work, they make use of BDOS secret sharing, because of which the communication overhead is n square kappa. We have a different view on how we can authenticate the random masks that are involved. And this view helps us to replace this BDOS secret share with PAC secret sharing, thus reducing the overhead by a factor of n. So in this talk, I'll be using the following notation, that is each wire is associated with a random mask RW. XW denotes the true value during execution of that wire, and rho W denotes the masked value. Now, in WRK protocol, the party P1 plays the role of evaluator, and the remaining parties play the role of garblers. And each party has a MAC key delta I, which is used for BDOS secret sharing. And for each wire, which is an input wire or output wire of the AND gate, the pre-processing samples a random bit RW and secret shares it among the AND parties. Then it makes use of BDOS secret sharing, as already discussed earlier. That is, each party's additive secret share is going to be authenticated to every other party. So here, the secret share R2 is going to be authenticated to party P1. Then R1 is authenticated to party P2, and so on. This way, I'll succinctly represent this collection of shares by the label BDOS. And for each of these wires, the garblers also sample a label uniformly at random. Then for each XOR gate, we have the invariant in the WRK protocol that the random mask associated with the output wire is just the XOR of the random mask associated with the input wire. And since the BDOS secret shares are linearly homomorphic, parties can locally XOR their shares to obtain BDOS shares for the output wire's random mask. And the garblers will XOR the labels associated with the input wires to obtain the label for the output wire. And to process the AND gates, you require this correlated randomness, which is R sigma, which is the AND of the random mask of the associated with the input bits. And the pre-processing generates a BDO secret sharing of this and shares it among the AND parties. So they have an instantiation of this pre-processing, which requires order n square kappa communication per gate. So the construction of WRK maintains the following invariant. That is, for each evaluated wire, the evaluator holds the masked value and the labels associated with this masked value. And coming to the evaluation of XOR gates, firstly, XOR gates are free in WRK, so the garblers do not need to send any garbled material. And for each of these XOR gates, the evaluator holds the random mask and the labels for the input wires. It simply XORs them locally in order to obtain the random mask for the output wire and the associated labels. This works because of the way we had computed rho gamma and X gamma in the R gamma and X gamma in the pre-processing phase. Now, the garbling of AND gates is slightly involved. So here you have each garbler holding the BDO shares associated with the random values associated with that AND gate. And it also holds the labels for the input and the output wires. Using this, it constructs a garbled circuit by linearly combining this BDO shares and appropriately encrypting it using the input wire labels for the 4-input combination, and it sends to the evaluator. I do not have time to go over it in detail, but the thing we need to take away here is that the size of each garbled circuit in this case is order n kappa. And we'll see why that is the case in the next slide. So here in the AND gate evaluation, the evaluator holds the masked value for the input wires along with the associated labels. It had received the garbled gates in the pre-processing from the garblers, and it holds its shares of BDO share for this AND gate. Using this, P1 first determines its BDO share for the masked value rho gamma, and it ungarbles the circuit by making use of the masked value. By making use of this masked value to identify which entry to decrypt in this garbled circuit, and using this input labels to decrypt that entry. So this way, it obtains the additive secret share of the garbler for that masked value, and the MAC components of the BDO share for that masked value, along with the output label XORed with the key components of that masked value. So here, because each entry holds this order of n many MAC components in the garbled circuit, the size of the garbling is order n kappa. So then once P1 obtains the shares, it verifies the consistency of all the additive shares using its MAC key delta 1. And once it is satisfied, it computes the garbled labels for the output wires such that the invariant holds to process the next gates. Now, in our protocol, we observe that the WRK construction obtains an authentication of additive shares of every other party's secret. We observe that this is not necessary. And in order to prevent the adversary from flipping the masked value, it suffices for parties to just hold shares of authentication of the value with every party's MAC key. I know this is a mouthful, but it will become clear with the visual representations in a couple of slides. But this observation of ours paves way to construct a scheme with PAC secret sharing. So in PAC secret sharing, we have a field of size at least n plus L, and given a secret vector x, it defines a polynomial of degree at most n minus 1, where at special points ai, the polynomial evaluates to the secret value xi, and for n minus L distinct points outside this space, the polynomial evaluates to a random value, and the evaluation of the polynomial at point ei is the secret share that is held by party pi. And the PAC secret sharing is secure for a threshold of t at most n minus L. And if L is set to epsilon n, and epsilon being less than half, we are in the dishonest majority setting. Now, coming to the pre-processing of our construction, the handling of the random mask and secret share is same as that of WRK. But this is the change that I mentioned, that instead of using Bido-style secret sharing, what parties hold is an authentication of the bit RW using the MAC keys of every party. And you can see that we can pack this, that is make you, the size of the shares is still order n square kappa, so we haven't improved anything in terms of concrete communication. But we can make use of packed secret sharing to pack this authentications into single polynomials, and this way we obtain constant many polynomials that packs this authentications. Now, each of these parties also sample a random label xiw, and in this case, P1 also samples a label, and this is because this label also acts as the key component of the Bido's secret share. And in order to process the garbled circuits compactly, we also require packing of these labels so that the size of the garbled circuits do not blow up in the computation. Then the handling of XOR gate is essentially the same because packed secret sharings are also linearly homomorphic. And along with XORing the input labels, parties also XOR the packed labels. Then for each AND gate, the pre-processing computes R sigma, the correlated randomness R sigma, and it distributes a packed secret sharing among the AND parties. And though I don't have time to discuss a pre-processing protocol, it is quite involved. It uses tricks from share transformation of packed secret sharing literature, and also makes use of consistency checks to ensure that the inputs to the two parties across multiple instances for different parties is consistent. And also ensures that the overall communication cost of the protocol is order n kappa per gate. Our protocol maintains the same invariant as that of WRK. Now, the garbling of AND gates is more or less the same. It's slightly different, but it's just that instead of using Bido secret share, we make use of packed secret sharing, which allows us to have garbled gates of size order kappa. And coming to the evaluation of AND gates, the evaluator uses the masked labels to decrypt appropriate entries that is pointed out by the rows corresponding to this masked value. And using its shares of packed secret sharing associated with the AND gate, it obtains the additive secret shares of the masked value rho gamma and the packed secret sharing of the associated labels. Now, from each gate, since it obtains only order of kappa many information, the size of Garble's gate is order kappa. And party reconstructs this value rho gamma, and it reconstructs all the associated labels and verifies its label with respect to delta 1. And this ensures that the invariant also holds for the output wire of AND gates in our construction. Now, coming to the communication cost analysis of our protocol has the least communication for n equals 32 to n equals 7,000 parties because the communication cost of BGH is constant, has constant overhead. So for instance, for n equals 32, we are 1.7x more efficient than Goel et al.'s work, 7.3x more efficient than BGH, and 81x more efficient than WRK. And the break-even point, even though BGH plus is a constant communication protocol, only it starts performing better than our schemes when n is greater than 7,000. And coming to the size of garbled circuits, our scheme has the most efficient garbled circuit, and it is 7x more efficient than the state of the art for n equals 128, and it's better for values of n equals 8 to 880. In the case of multi-party garbled RAM, multi-party authenticated garbled RAM, we make use of the result by Heath, Kolesnikov, and Ostrowski that reduces RAM computations to tri-state circuits. And these tri-state circuits have gate evaluations that depend on the input. So this may leak some information about the input, and as a result, they introduce this notion of oblivious tri-state circuits that also takes some randomness as input that ensures that this order of execution do not leak any information so that this execution order remains simulatable. And they show a reduction that exists in oblivious tri-state circuits of size order T log cube that simulates t steps of a RAM program. And using this result, and the result for our garbling schemes for Boolean circuits, that is, we first extend our idea of garbling Boolean circuits to also garble tri-state circuits. And then this way we obtain a garbling scheme for tri-state circuits with order n kappa overhead. And using the result of Heath et al., we are able to construct a multi-party garbled RAM with n log cube kappa communication overhead. So to conclude, we obtain a concretely efficient, maliciously secure multi-party garbling scheme that makes black box use of lightweight crypto primitives and that has concrete communication efficiency. That is work by Goyal et al. In this conference that constructs a multi-party garbling scheme with constant communication overhead. However, the focus of this work is an asymptotic improvement, and our scheme is concretely efficient for moderately sized circuits and moderate number of parties. Their scheme starts performing better as the number of parties and circuit size grow. So coming to the open questions, it would be nice to obtain a concretely efficient garbling scheme where the communication overhead is just constant, or obtain the same result as ours, but in the strict dishonest majority setting. Okay, yes. With this, I conclude my talk. Thank you.
Do we have any questions? If not, I will start with a question. So you don't have a strict dishonest majority. You have like a 1 minus epsilon corruption threshold. So when you showed your comparison of the communication costs, like what was the specific threshold that you were using for that slide?
So in our case, our results have been reported for n equals 1/4. That is, sorry, for epsilon equals 1/4. So the number of corrupt parties is 3/4.
Okay.
And here WRK's result is for n minus 1. But despite of that, if we have factor, where is it? Yeah, if we have this factor by 4 by n, we are still performant. Like we read.
Yeah. So how sensitive?
20,
How sensitive is
more.
the performance to this epsilon parameter? Like if epsilon is very small, does the table look significantly different?
Yes, if epsilon is small, then our scheme will start performing worse. But if you consider that threshold for t equals 3/4, if you want to use it for that setting, in WRK construction, you will have to secret share the input wires of parties that are not going to be involved in the garbled circuit, and you have to reconstruct it within the garbled circuit. So that is an additional n square I overhead for that setting.
If there are no other questions, let's thank the speaker again. All right, the last talk in the session is about picogram, depending on how you like to pronounce that. Practical garbled RAM from Decisional Diffie-Hellman. It's a paper by Tianyo Gu, Afonso Tinoco, Sri Harish, Govinda Rajan, and Elaine Shi. Tianyo will give the talk.
Thank you for the introduction. I'm happy to share our work picogram, a practical garbled RAM from Decisional Diffie-Hellman. So I think previous speakers have made a pretty good explanation what garbled circuit is, but just let me rephrase it quickly. So in the protocol, we have a garbler which receives some circuit and turns it into a garbled circuit and send it to the evaluator. The evaluator also gets the input of the circuit, but in an encoded form, and it computes the output of the circuit. So for security, we want to ensure that the evaluator learns nothing about the circuit's input. And yeah, so the most well-known construction is by Yao in 1986. So in Yao's garbled circuit, we assign 2 keys, or sometimes called labels, to every wire. And to garble a gate, we just encrypt the output label with the input label. So here, each label corresponds to either bit 0 or 1. And in cryptography, we like circuits. But in real world, we have much stronger computing machines. Specifically, we have a CPU that can make like arbitrary access, like read and write access to a memory. So a natural question is whether we can replace a circuit with a random access machine program. So here it's a gibberish program that make like index the array Y. So before I move on, let me introduce a bit of the history. So in about 2012, people first came up with this idea of RAM model two-party computation. So basically how two parties can collaboratively compute a RAM program without revealing to each other their inputs. So an efficiency issue with this early approach is that the run complexity depends on the runtime of the program. So basically at every time step, the parties need to make several rounds of communication, and it's very costly. So 1 year later, Lu and Ostrovsky proposed this work of Garbled RAM, which reduces the run complexity to constant, combined with oblivious transfer. So can we do better? Yes. So 2 years later, many people come up with this idea of succinct Garbled RAM, which also reduces the communication to constant. But like all the known constructions of the succinct Garbled RAM are based on I/O and are not practical today. So in this talk, we will just forget about it and consider how to make the Garbled RAM more practical. So here's a summary of our result. For simplicity, I assume the word width, basically the number of bits in each memory cell, to be moderately large. It's like at least log square, and where n is the number of memory cells. So as you can see, so for these prior works, they are getting closer, and the cost is getting closer and closer to this interactive baseline, while reducing the run complexity to just 2. But we are the first that actually matches the interactive baseline. So finally get rid of these like log factor and log factors. And if you are willing to ignore the security parameter lambda and also this arbitrarily small super constant factor, our result is actually optimal by the ORAM lower bound. Okay, let's go back to our RAM model. So it's helpful to think of a RAM program as a CPU plus a memory. So the CPU is just like a bunch of Boolean circuits. So at every time step, the CPU make an access to the memory and update its local state and pass it to the next time step of the CPU circuit, and so on and so forth. So the CPU part is easy. It's just a Boolean circuit. The problem is how to implement this memory. So the difficulty is that at every time step, the CPU can make some arbitrary access to like any location in the memory, and this cannot be predicted in advance. So if you want to express it as a Boolean circuit, then you have to make a linear scan of all the memory locations at every time step, and it's apparently not very efficient. So as the elegant work of his et al. Shows, we can actually model the memory by combining an ORAM, oblivious RAM, with a special primitive called stack. So here the ORAM is just a bunch of Boolean circuits again, but the stack is actually the part that captures the unpredictability I just mentioned. And in fact, in all the previous works, the stack is the performance bottleneck. So what is a stack? You can think of it as a simplified memory that only supports 2 instructions. So at every time step, it either accesses like the next memory location, or it just performs nothing, just no op. And moreover, since we are already using an ORAM, it's fine to reveal to the evaluator like what instruction is performed at every time step. So here, for simplicity, I assume all the accesses are write accesses. So you can, we only need to pass the data downwards, but later you are seeing our construction, we can also pass the data backward. Okay, this is seems to be simpler to implement than full-fledged memory, but can we make it even simpler? So how about we just consider the minimal case of the stack? Let's say there are just 2 input time steps. We'll use X and Y to denote the input Y at each time step. And so in these 2 time steps, like only one of them will be a real axis and the other will be no op. So here we use another YC to specify which of the input time step is a real axis. So in the first case, C is 0, so we want to pass the data from YX to YZ. And in the second case, we want to pass the data from Y to Z. So just to clarify, this selector should not be thought of as like a Boolean circuit with 3 input wires and 1 output wire. So the difference is that in like a Boolean gate, you only evaluate the gate when all the input wires are set. But here, like in case 1, you notice that we don't need the wire Y to be set before setting the output YZ. So in a sense, it is this kind of partial evaluation behavior that differentiates this RAM model with like a regular Boolean circuit. Okay. So here's a selector in the real world, like a railway merge. So how to gobble a selector? As the previous work shows, we just need to encrypt the difference of the input and output wire labels with the labels of the control wire. So at runtime, if say C is 0, then the evaluator get this label, right? LC equals 0. It can decrypt the XOR of the label of LX and the LZ. So it can get the corresponding label of YZ from YX. And similarly, if C is 1, it can get the label of Z from the label of Y. Okay, so far we have assumed that the selector is only used to select a single bit. But in practice, we need to select like multiple bits in a memory word. So here we have a communication that's constant, but if we want to select like W bits, here, if you do it naively, the cost will also grow with W, right? So this kind of primitive is like we use a single control wire to select like multiple data bits. It's often called single instruction multiple data, SIMD for short. So we're wondering how we can improve this. So I want to mention that one alternative approach here is just to merge these input wires into a single wire and use arithmetic gobbling. Basically, we let each wire carry a larger integer value rather than like Boolean value. But the drawback of this kind of approach is that once you gobble an arithmetic wire, it's much like more expensive to get the wire like decomposed back to the Boolean wires. And the existing approaches for arithmetic gobbling are still pretty expensive computationally. So we want to avoid that here. And we want to keep these wires still separate and each carrying a Boolean value. So how do we do? So first, I would like to introduce a simple lemma. It's called matrix DDH, but please don't confuse it with matrix DDH assumption. That's a different thing. So here is a common definition of DDH. So basically, it says if you sample this S and K randomly, then this G to the SK will be just like a random group element, even if the distinguisher has this G to the S and G to the K. So with DDH, we can actually show that the matrix below here is pseudo-random. So to see it, you can actually just replace every entry of the matrix one by one using DDH. So this matrix, which is like a rank 1 matrix on the exponent, we can show that it's pseudo-random. And for simplicity, I will just write G to the SI as GI. So we'll use this matrix. And spoiler alert, we'll use it as our Y labels. Okay, so let's see first how we can gobble a single bit selector using this DDH approach. So for each wire, we'll sample a different key on the exponent, but we will use like uniform G0 for all the zero labels, and use G1 for all the one labels for all these wires, for all these data wires. So here, now to garble this gate, we just encrypt the ratio of this exponents of the input and output wires. So as you can see, if say at runtime, if C is 0, then the evaluator get KZ over KX. So it can just take the label for X to this KZ over KX power and get the label of YZ. And now you can see that the garbling material here does not depend on G0 or G1, right? So we can actually reuse it for multiple wires. So now we assume there are like wires of like a group of W wires, and we will use G sub 2i and G sub 2i plus 1 as the base for the i's offset in each word. And we will use the same like KX here for all the wires in a single memory word. So the evaluator can still get the labels for every wire in this ZI from the label of XI. Okay, so the main takeaway is here the communication cost does not depend on W. But how about the computation cost? It seems that the evaluator still needs to compute every of these output labels by doing an exponentiation. So to understand how we save computation, at least asymptotically, it's good to see how we build the stack from the selector. So in prior works, they actually used a hierarchical data structure called the oblivious stack to build this stack. But we realized that it's actually suffices to use just an oblivious compaction network to achieve our stack. And it's like concrete improvement that gives us about 4x reduction in the circuit size and also in the number of lines of the pseudocode. So it's just a nice trick. So how does it work? So basically, we decompose the stack into a network with log n number of layers. So at each layer, the entry can either stay at its own original location or move left by some amount. So at level 1, we can move left by 1 unit, at level 2 by 2 units, at level 3 by 4 units. So Goodrich shows that this kind of network ensures no collision. So it actually works for our use case. And if you look at it carefully, it's actually just composed of n log n selectors. So now back to our question about computation. We realized that if you are connecting these selectors in series, then neither the garbler nor the evaluator needs to compute these intermediate labels, like here, the LY. So for the garbler, because it samples these KX and KY by itself, it can just compute the ratio. And for the evaluator, it can just first compute the product of all these exponents and then do a single exponentiation. So the number of exponentiation does not depend on the network depth. Okay, finally, for the concrete performance, we achieve about a 2.5x improvement over prior work if you count the end-to-end time. And here, like for memory space 2 to the 16, we achieve RAM with about 6 instructions per second. And if the RAM becomes larger to like 2 to the 30, which matches some like interesting real-world use cases like Signal's private contact discovery and Ethereum balance tracker, the RAM frequency drops to about like 1 point something instructions per second. But one nice thing about garbled RAM is that actually the garbler can send the garbled circuit to the evaluator in advance. So if you allow this kind of pre-processing, then our garbled RAM can achieve a frequency of about 100 Hertz and for n equals 2 to the 16 and about 20 for n equals 2 to the 30. And for people who care more about communication, we actually achieve a very big improvement over prior works. And as you can see here, our communication is already very close to the interactive baseline, while we just can't cut the run complexity to constant compared to the baseline. So for future work, we would like to see like more speed up, of course. And so right now our work assumes semi-honest setting. So it would be interesting to see how we can extend it to malicious security and also adaptive security. And as the previous talks mentioned, people want to instantiate this in a multi-party setting. And we are also interested to see whether we can weaken the assumption. So right now we are based on DDH. Okay, thank you. So here's an open source code of our Garbled RAM, and thank you for your attention.
We have time for questions.
Whether the concrete performance is like the bottleneck is it the group exponentiations, or is it like AES or those like operations?
Oh, it's a very good question. So in prior works, usually people assume that the concrete performance depends only on the communication cost, because like with the modern hardware, AES is just so quick. But here, because yes, you mentioned like we are using exponentiation, and actually we are using like 256-bit elliptic curve. So it's not as fast as AES, but actually this allows us to get a better balance between the communication and computation cost. So yeah, so you can think of our work as like using some lightweight cryptography and getting savings in communication and with like some additional cost in computation.
Okay, thank you.
Yeah, thanks for the question.
So if I understand correctly, it's the use of the SIMD circuit that gets you all of your advantages. Is that only possible because you do this compaction, this oblivious compaction thing, or is there a parallelism sort of already available in the HKO paper?
Yeah, I think in the previous paper, they used this oblivious stack construction, and our trick also applies to their scheme. It's just the oblivious compaction is a bit like simpler in the structure. So
do you get more parallelism from the oblivious compaction, or is it just simpler in general?
We don't get more parallelism. So the parallelism just depends on the word width.
Okay, thanks.
All right, let's thank the speaker and all the speakers in the session. Now have a 1 hour break. After the break, we'll resume back in Corwin Pavilion for the award paper session.